Okay, so we have already taken 2 lectures on logic. Today I will do only few things in logic. Probably half of it, half of the lecture will be on the rules of inference. So what is that rules of inference? I will explain to you. And after that is one topic on normal form. But I think I will skip it. You can look at it the last year video for that. It's just few minutes because I think so. I will be then covering or rather starting a most beautiful part of your you know discrete math part. Okay, and so in order to do that, I have to cover certain basics in mathematics, which you know already, probably set theory, functions, relations, and so on, right? I just quickly review that. Then I will talk about you know a general architecture for computers. What are the computers and how do we look like? Theoretically, how we should look at computers. And all this. So the next 5 lectures from today, after today, will be focused on models of computation or introduction to theoretical computer science. It's a very, very fundamental subject. Anybody who has done BTech in computer science or, this course is compulsory course. Unfortunately, or fortunately, whatever you say, in our place, it is an elective course. Okay. Some people take it, some people don't take it without realizing the power of it. It's very, very important. So suppose you want to construct a compiler or that kind of, things, this course is going to be very useful for that, Normally models of computation is a very important course. What I will do, because otherwise this course is about 40 lectures, I cannot give 40 lectures to you. So Shastra Anant hai Vidya ka parabar nahi hai, right? So we should look at fundamental things. I will just summarize everything in approximately 5.5 lectures. I will give you a broad overview so that you have very good understanding. Later on, even if you don't do the course, you are fine because you know the basic concepts. Okay, it's very, very important. So before that, let me finish this one topic in logic. Let me check everything is fine. Okay. So logic, now I'm going to talk about how do we define. So we talked about propositional logic, right? What are the propositions? They are either true or false and so on and so forth. Now, collection of propositions actually is called argument. Now, argument will have bunch of propositions, right? One proposition, or I would say that the final proposition in that argument is always a conclusion, because whenever you are doing argument, there will be a conclusion, right? So there is a conclusion, and before that, whatever propositions are there, they are known as premises. So using some of these premises, which are small propositions, and its final conclusion, the whole thing is known as argument. So the question is, if there is an argument given, or in fact a much more broader term has been defined known as argument form. Okay, that kind of stuff is given to you, and you want to check truth or falsity. So how do you check? You make tables and do all those things, right? But the table is a tedious job, right? And it's very complicated, and making tables will be a very tedious job. So people have come up with an ideas, what is known as rules of inference. Okay, using rules of inference, you can simplify the things, and actually you can reach the conclusion faster. So that is what all about rules of inference. Okay, so I'm going to talk about rules of inference. Okay, there are about a couple of rules there, which I'll tell you. If this is there, this is there, then what is the conclusion? If this is there, what is the conclusion, like that, right? And so that will simplify. Okay, and then also finally towards the end, I will talk about resolution principle. So resolution principle also, to simplify the argument, there are, so if there is a proposition P and there is a proposition negation of P, so how we can cancel out their effect and so on, while doing the calculations, so simplification. Okay, so these two things I am going to talk about today first. After that, I'll give you the basics of maths that is required to understand models of computation. Clear? So let me start. Okay, so the topic is rules of inference. So I need to define argument. As I mentioned to you, what is argument? Argument is a sequence of propositions. Okay, in proposition logic, right? And as I mentioned, all but final. All propositions other than the final proposition, which is the conclusion, right, are known as premises. Okay, and final one is final proposition is known as conclusion. Okay, so argument, collection of propositions, right? And in that or sequence of proposition, I would say, because one sequence will give you another sequence and so on and so forth. So all except the final proposition, which is known as conclusion, all other propositions are known as premises. Okay, fine. This is some basic terminology. Now, yes, same link is there, but good. So you are telling 1 minute, 1 minute. Okay, thank you. So I think it is there now. Yeah. So argument is sequence of propositions. Okay, and all but final propositions are known as premises, and final proposition is known as conclusion. Then we want what we want to do actually. An argument is valid argument is valid, okay, if truth of all its premises implies that conclusion is true, which is obvious. So argument is valid argument if all the premises are true will imply that conclusion is true, right? Then we say that argument is valid. Fine. This is what I mean. This is what the business that you want to do all the time. Now, a much more generalized term is known as argument form. What is argument form? Is a sequence of compound propositions. Okay. And involving proposition variables, a sequence of compound propositions involving, you know, propositional variables. And of course, again, the same thing, if premises are true and they will imply conclusion is true, that means it's a valid argument form. So whenever we want to verify some of these complicated things, actually through truth table, it's very difficult. You know, it takes a lot more time. It's tedious. So we need to come up with some simplifications, right? How do we simplify? So actually now I'm going to give you what is known as rules of inference. Okay, there are certain rules which if we use, it is easy. I'll give you a couple of examples after that, you know, how we can simplify the things. First of all, first a small example. P, you have a current password, and Q is another proposition. You can log onto the network. Okay. So the question is, if I am asking P implies Q, is it a valid argument? P implies Q, is it a valid argument? Okay. So how do we verify? We need to some calculations, not very difficult. I will show you. Now we know that both P implies Q is and P is true, right? So therefore Q must also be true, right? Because so what we write it like P implies Q, P both are true, therefore Q is true. This is shorthand notation for writing this. This is true and this is true, right? So therefore Q must also be true. Okay. And so we write it like this. P implies Q is true, P is true, therefore Q is true. This is our rule of inference kind of thing. Okay. I will make more concrete examples, or in fact the basic ones I will give now. Okay. So this is how, so this is a, so that means this is a valid argument, right? Argument is valid. So basically you should note that here, you know, we have used this fact that P implies Q meet P, Q is a tautology. Right? So this is true all the time. So basically I can write it as a fact. When we observe this, a fact is an argument form with premises P1, P2, Pn, and conclusion Q is valid when P1, P1 and P2 meet Pn, Q is a tautology. Okay. So this is the fact. Actually, we have just shown the example. So an argument form with premises this and conclusion this is valid when this is a tautology, right? So now I think I am ready to give you the basic rules of inference. So the most important one, actually I should mention first, is known as modus PONENS, modus ponens. This is the most important one. also known as law of attachment. And the basic is P meet P going to Q. Q is tautology. Right? So that means P implies Q, therefore Q. P is true, P implies Q is true, therefore Q is true. Okay. So this is the basis. Okay, so this is the first one. I can make a table actually now. So in the table, I will mention about what is the tautology, what is the name of the rule, and this symbolic form. I will not write too many statements, but I will make 3 columns actually to tell you what is happening. Okay. And so you need to kind of, if you do a lot of practice, you remember them. Otherwise, you have to memorize. There is no other option, right? But if you do use some logic, you can obtain, yes, right? Any question? Okay, so here is the table. Rule of inference, tautology, and the name of the rule. The first one, P implies as Q, therefore Q. P is true, P implies Q is true, therefore Q is true, right? So this say that P meet P implies as Q. This is the tautology. The name is modus. This is the name. Next, negation of Q is true. P implies Q is true. Therefore, negation of P is true. So, rule is negation of Q meet P implies Q. Implies negation of P. Modus. These are just names, Next, P implies Q is true. Q2 implies R is true. Therefore, P implies R is true. Right? Which is also okay. So in terms of tautology, we say that P implies Q. Meet Q implies R. Implies R. This is known as hypothetical SYLLOGISM. Fourth one, P join Q is true. Negation of P is true. Therefore, Q is true. Okay. So this is join Q. Meet negation of P implies Q. This is known as disjunction. Okay. So these are 4 of them. I will write a few more. So I think the first thing tells you many things straightforward, right? What is happening? We do some analysis. So I'll just complete the table actually in front of you. Next rule is addition. P, therefore P union Q. If P is true, therefore P union Q is true. I mean P join Q is true. Okay. So tautology is join Q, meet negation of P. Sorry. This one. P implies P join Q. This is a tautology. This is known as addition rule. Okay. Next, P meet Q is true, therefore P is true. This is P join Q going to P. Simplification. The name is simplification. I think the use of this will be more clear when we do a couple of examples. Okay. Next, P is true, Q is true, therefore P meet Q is true. This is P meet Q implies P meet Q is conjunction. Huh? 1 minute. Second one means what? The simplification, right? 1 minute. I think there is a yes. It should be meet, right? Okay, this one is conjunction. And last is P join Q, negation of P join R, therefore Q join R. This is resolution. I think while writing so many things, I may do mistakes. So please note that. I mean, you can always correct it. Negation of P join R. Guys, Q join R. Okay. I will show you about the resolution anyway. So let me do some examples. So then it will be more clear what is happening, right? Let me look at. Okay, the first example. Find the rule of inference in the following argument. Argument is it is below freezing now. Therefore, it is either below freezing or raining now. I have to find the rule of inference. Statement is it is below freezing now. Therefore, it is either below freezing or raining now. So P is it is below freezing now. And Q is it is raining now. So that means we have P, therefore P join Q. This implies that argument is using addition rule. P is true, therefore P join Q is true. Okay, using addition rule. Let me do 2 more examples actually. It's 1 more example. Find the rule of inference. Okay. The statement is, it is below freezing now. It is below freezing and raining now. Therefore, it is below freezing now. So P is, it is below freezing now. And Q is, it is raining now. So here the rule of inference is P meet Q, therefore P. If P meet Q is true, therefore P is true. So using simplification rule. I think. Okay, so there are a few more examples which I think I have done last time, but I am skipping this time. You can look at it. We have, because I have to cover a few more things, but okay. So I hope this much. So this table is important, and then you can do some examples. Okay. So next 10 slides, I'm going to use Professor Bush from Louisiana State University with permission. So I have taken permission from him to use these slides. These are pretty good slides. And making them is a difficult, it consumes a lot of time, right? So it's better to ask them, like, can I use it? So these are pretty good slides. I'm going to use it to cover theoretical computer science basics, okay? The first thing is that some mathematical preliminaries, which probably most of the stuff. Sets, functions, relations, graphs and proof technique. Proof techniques you might have done in the calculus, right? No? Okay, so we can do it quickly. Graphs I will skip because graphs anyway I am going to do it in detail towards the end of the course. Set is a collection of objects, right? Fine. Well defined means, I can tell whether something is in the set or not in the set, right? Which is very clear. Set representation, finite set, infinite set, so on. This already, right? Now you just enjoy. You don't have to sleep. You can watch like a movie, right? So universal set. So there is a set A, and then there is a universal set containing everything, right? A is a subset of universal set. Every set is subset of universal set. Set operation you can do union of two sets, intersection of two sets, difference A minus B, all those elements in A which are not in B, right? Like that. Similarly, B minus A you can define. Okay. Complement. If A is given, complement with respect to universal, you can find whatever elements which are not in A but are in U, right? You can find them. For example, set of even integers, complement is odd integers. If integers is the universal set. De Morgan's law, this also A union B, complement is A complement intersection B complement, and so on. Phi is a null set or empty set. S intersection phi is S. S union phi is, sorry, S intersection phi is phi. S union phi is S. Fine. S minus phi is S. Phi minus S is phi. All those elements which are in phi, which are not in S. And the complement of phi is a universal set, which is also okay. Yeah, so there is some beauty here. You can say subset. So we know that A is a subset of B if number of elements in A is also a member of B, right? So now we have proper subset if size of A is less than size of B, then it is a proper subset, right? Otherwise improper when the size is same. Now we know that set of integers we know Z 0 plus minus 1 plus minus 2 and so on, and 2Z set of even integers, right? So 2Z is a subset of Z. 2Z is a subset of Z, but they have same number of elements. How it is possible? No, but you see the problem, what I am telling you? A is subset of B, right? So number of elements A should be less than the number of elements B. But here the number of elements are same, still A is a subset of B. This is the beauty. You have to give some thoughtful answer. No, every element, every member of 2Z is a member of Z. Agreed? Yeah, it has to be. What do you mean reverse is not true? Reverse की तो बात ही नहीं कर रहे हैं हम. I am just saying that A is a subset of B and number of elements in both the sets are same. So actually there is a Hilbert Hotel. Have you heard of Hilbert Hotel? Hilbert Hotel has infinite number of rooms, and you know that everything is packed, nobody is there. Suddenly there is a bus full of marriage people. They came, and so there are about 30 people. They said that I want get a room in the hotel. So the person said that, sorry, everything is full. It looks like Hilbert was there in the bus. He said that, okay, it's very simple. What you do, just ask each one to shift the room, 30 times, right? So you shift everything, so 30 rooms will be vacant and you can go there. This is the Hilbert Hotel, right? Problem, the issue is that because there are infinite number of elements, and that's why it is counterintuitive. Because number of elements are infinite. If it is finite, then yes, size of A is strictly less than size of B. But this is infinite. Infinite business is pretty beautiful, right? Because you know that George Cantor, when once he wrote a paper on different kind of infinities, people said that he's mad guy, what he's talking about. Later on, they realized that he's written beautiful thing, right? So I mean, you have to observe the beauty anyway. Disjoint set when there is nothing common, right? Cardinality of the set, number of elements in the set. This is also okay. Power set. This is also very important for programming. Power set. Whenever you might be doing programming, if you are doing competitive programming, even you must have encountered power set. And power set. So is if S is a set ABC, power set is set of all possible subsets. So you see that Y, A, B, C, and all this. Good thing is that everything can be written as a binary, right? If the elements are, you say that if A is there, I will write 1. If B is there, I will write 1. If C is there, I will write 1. Otherwise, I will place 0. So everything, so phi is nothing is there. No A, no B, no C. This means only A is there. This means only B is there. This means only C is there, and so on, right? So actually, power set can be represented in the form of bits. Very useful for programming. Competitive programming. Maybe I should offer a course on competitive programming sometime, right? How many people will take? Everyone? Because that is very, very important anyway. Let us see. So the size of power set is 2 raised to power size of S. Cartesian product A cross B. So Cartesian product of A cross B is cardinality of A times cardinality of B. This is also straightforward. You can generalize to more than 2 sets. Functions. What is function? Can anyone give a definition of function? ये तो बहुत बार पढ़ा होगा, कैलकुलस में पढ़ के आए हो. Function is a rule which associates to every member of a set, giving unique image in another set, right? That is a function. So if I say that f of x is equal to square root of x, is it a function? You have to be sochna. By the way, once there is a question about functions, if I define a function and I'll ask you, although it is not a calculus class, but probably you can look at it. Function f of x is defined for every real number x such that you take a real number x, write down its decimal expansion, right? If in the decimal expansion of x 7 consecutive 7s comes, the value of the function is 1, otherwise 0. Got it? Function is defined on the real numbers. Now what we do? Write down the decimal expansion of x, because every real number has a decimal expansion. You write down the decimal expansion. If in the decimal expansion there are consecutive 7 occur, then the value of the function is 1, otherwise it is 0. You can do that. Being a mathematician, you can define whatever you want, actually, and people have to follow. Yeah, it's true. I mean, recently, if you read one of our paper, we have used Gauss distance. Gauss means cow. Find it Gauss distance, and now people are calling it Gauss distance. So it is up to you what you define, right? This is how you define a function. Okay. And so the question is, discuss the continuity of this function. Don't you think it's a beautiful problem? So maybe, but it's not a calculus class. Sometime you can look at it anyway. Okay. So there is a domain, there is a range. Relation is a generalization of function, right? Function is a specific kind of relation. So any subset of the Cartesian product x cross y is a relation. ये तो सब पढ़ के आए हो ना, इंटर में पढ़ा होगा, राइट? 10th or 12th high school में, I think it's in high school. Anyway, so relation, and there are 3 kind of relations. Reflexive relation, x is related to itself. Symmetric, if x is related to y, then y is related to x. Transitive, x is related to y, y is related to z, then x is related to z. So T time problems. How many reflexive relations are possible on a set with n number of elements? How many reflexive relations are possible on a set with n number of elements? How many symmetric relations are possible? How many transitive relations are possible? Beautiful problems for a cup of tea. Enjoy, right? Yeah, so I don't know the answer, you right? Okay. By the way, once all the 3 properties are satisfied, you can partition the set into what is known as equivalent classes. I have covered in second lecture one such example. Can you tell me what is that example? Which is example of equivalent classes. So which partition the whole set into equivalent classes. Second lecture, if you remember. Very simple, integer modulo 2, having 2 numbers 0 and 1. 0 is actually equivalent class. and 1 is another equivalent class. 0 is equivalent class means all the numbers which will give you remainder 0 belongs to in the 0 class. All the numbers which will give you remainder 1 belongs to 1 class, right? So 0 and 1 are equivalent classes. So basically, this congruence business, A is congruent to B mod n, is an equivalence relation. And that's why you can partition the whole set of integers into these equivalent classes. So integers which have remainder 0, integers which have remainder 1, integers which have remainder 2, 3, and so on, right? They will, you can partition the whole set. It's a very natural example of equivalent classes, right? So this is all about equivalence relations. So equivalence classes, as you see, graph we can skip. I think proof by contradiction, let me do first for you. Proof by contradiction, Pada hoga, but I'll just quickly. We want to prove that a statement P is true. So we assume that a statement is false. Then we arrive at an incorrect conclusion. Therefore, the statement P must be true. This also you must have read. Square root of 2 is not rational. So whenever we are talking about rational, irrational, one question that comes to my mind is pi. Beautiful number, right? Pi is a very beautiful number. You see, you look at all the rivers on this planet, okay? Their source, their destination, and you measure the actual distance, I mean the distance with respect to line, and whatever the curve they take, and it turns out that the average of all of them turns out to be pi. Beautiful thing, right? Similarly, you take a plain paper, draw two lines, parallel lines, and you drop a ball pin or pen, whatever, and you can compute pi. You know that how? Beautiful things. But one question that one can ask, pi you take 22/7. Pi is rational or irrational? But why we take 22/7 then? Approximation, good. But why can't, suppose we write pi is equal to p by q, where p and q are integers. What is wrong? If I write, is it possible? ब्रह्मांड में कहीं भी चले जाओ, actually, if you draw a circle, measure the circumference and the diameter, and the ratio turns out to be pi. This is such a beautiful thing that the spacecraft, Marian 7, I guess, the Pioneer 10 spacecraft, which went to, outside our universe, our solar system, is actually emitting the value of pi, because the aliens will know pi if they, because without pi they cannot survive, right? Pi is such a beautiful thing. So anyway, so this is all about root 2, all this anyway. So this is all done. So like that, now next movie starts in 1 minute. Again, thanks to Professor Bush, he's made nice slides for me. Okay. So now actually we are going to come model of computation or introduction to theoretical computer science. This is the course name. There is a one very famous book written by Hopcroft, Motwani, and Ullman. Rajiv Motwani, have you heard of Rajiv Motwani? Oh, poor guys, right? Google, So those two PhD students who who are the founder of Google, was working with Rajiv Motwani at Stanford on this project. They did this project with Rajiv Motwani, and Rajiv Motwani then asked them to form the company, because this is fundamental thing, right? So Rajiv Motwani is no more now. Actually, he died in swimming pool. He got a heart attack a couple of years ago. But his wife is still involved in a lot of startup things. Okay, so yeah, so that's the fundamental thing. So he has written a book. So you must read that book, Hopcroft Ullman. I don't have this book here, but yeah, maybe someday I will show you. Very beautiful book. And there is another book by Michael Sipser from MIT Press, Theory of Computation. So this book is also beautiful, but I love the other book actually, Hopcroft Ullman. Huh? Yeah, I can show you the picture. What else? This is the book, Introduction to Automata Theory, Languages and Computation. Oh, this is book is also there. I'm sorry. You should watch this. 700 rupees only. Introduction to Automata Theory, Languages and Computation. Only line left, yeah. But this is on Flipkart. On Amazon, you will find more. Right? Beautiful book, actually. So if you really, you will love the stuff, what I'm going to cover. And this is something very beautiful book. I love it, So Rajiv Motwani, Ullman, and of course. Okay, so let us look at this. So we know that in computers we have CPU, right? And some memory. This you might have read in high school or maybe in class 6th, 7th, 8th IT course, right? So now there are different types of memory: temporary memory, program memory, input and output, right? These are the four things, right? This is CPU, input, output, program memory, and temporary memory. How they work? Let me show you with an example. If f of x is equal to x cube, so compute x into x, this is program memory, and compute x square into x. In the program, you can write, right? So now for a given input, say x is equal to 2, you know that temporary memory will compute this as per the program memory. Z is equal to 2 into 2 is equal to 4, and f of x is equal to z into 2 is equal to 8, so output is 8, right? That's what you do. This is how the computer works actually. The question is, what is so fundamental, or I would say, what is the beautiful thing in the computer? What is the most beautiful thing in a computer? See, CPU, right? And now, being a mathematician, I don't want to look at all those circuits and those transistors and so on and so forth. I can think mathematically, okay? And so I'm going to convert into a mathematical problem. And actually, the you if you actually you might have seen vending machine, right? Vending machine. You put a coin and you get a Coca-Cola, right, or whatever, or biscuit. So now, how it works? So in the vending machine, if you put something, how it works? The brain is actually a very simple machine known as finite automata. So I'm going to talk about finite automata. It's a very simple machine. This is also the brain of this elevator. Elevator you might have used for going up and down. There also finite automata brain is implemented actually. Simple kind of machines. So the whole summary of computer science is there are only four kind of machines possible. Only four kind of machines possible. One, finite automata. Second, push down automata. Third, linear bounded automata. Fourth, Turing machine. ब्रह्मांड में कहीं भी जाओगे ये चार मशीन मिलेंगी. So that's very important thing, right? So only four kind of machines possible. Such a beautiful thing, right? Now each of these four machines accept certain kind of languages. Each language has a grammar. Beautifully, I mean, most interesting thing is that this classification was discovered by Noam Chomsky, who is a linguistic professor. In 1956, he gave this whole classification of computer science. See the beauty and connections. Everything is connected to everything through mathematics, right? So you can see that. Okay, so this is really interesting. So let me show you in more details about finite automata. So automation, so this whole thing is known as automation, right? So actually what happens in the automation, there is an input and there is an output and something happens in between. What happens? Actually, for each input, a state is changed from one state to another state. That's what happens all the time in the automation. Here is the state. So CPU plus program memory is nothing but states plus transitions actually. Mathematically, we can say that we are in this state, there is a transition, we go to this state, from here we go to this state, and so on, right? This kind of relationship is there. So as I mentioned, different kind of finite automata, there is no memory. That's the beauty, there is no memory. Push down automata, there is a stack memory. Stack, have you heard of? और वो सब आता यहाँ से actually, right? Stack memory. And then there is a Turing machine, which has random access memory. Yes. Automation is kind of a automated kind of machine, basically, right? Which is processing something, some input. So no, so basically, I'm saying that just say in the vending machine, what happens? So this is also that is also a machine. Theoretically, what happens when you put some input based on the, so in automation, what automata machine does, it accepts a certain input and produces certain output. Okay, and in between, in the machine, what happens? Typically, state changes from one to the other state, depending upon what kind of a state is and so on. All those details will come soon. Okay, so Turing machine is random access memory. Which machine is missing here? I told 4 kind of. There are 3 only. Linear bounded automata, LBA, is here. So basically, this is the smallest beautiful thing, little bit more beautiful than this. Linear bounded automata is more beautiful than this, and Turing machine is the most beautiful thing, right? Turing machine is so powerful thing, concept, People after, I remember Professor Jagdish Srivastav, I met him in US. Once he read about these concepts, he started believing in God. Such a powerful thing. So it will change your outlook completely, because what happens? You think that, so why this is least beautiful than this? This can solve certain kind of problems, but then there are certain problems which this machine cannot solve. Next machine can solve whatever this can solve, but some additional problems it can solve. Linear bounded automata can solve whatever problems can be solved by this machine and some more additional problems. Turing machine can solve everything, whatever these people can solve, but still there are certain problems which Turing machine cannot solve. So there is a barrier, which is known as Turing barrier. And since there are only 4 kind of machines in the whole universe, in fact, somebody has shown that our universe is a quantum Turing machine. Okay. So beautiful thing. So anyway, so this is all about Turing machine. More flexible memory results to solution of more computational problems. So as I mentioned, elevators, vending machines, lexical analyzer for small computing power, these are all examples of finite automata. Temporary memory is not there. Finite automata, input, output, and state change. That's all. This is an example of finite automata. Push down automata, there is a stack memory. Push and pop, push and pop. You take some input, push, pop, and so on. So beautiful example, parsers for programming languages. Okay. So how this and that you can read into your computer science course. Turing machine, random access memory, input, output. So any algorithm is the highest known computing power is a Turing machine. So as I mentioned, less power, more power. That solves more computational powers, hardest problem, more complex problems, simple problems. This is a simple classification. Normally, linear bounded automata is a special kind of Turing machine. That's why people don't write it, because it's a special kind of Turing machine. That's why only they mentioned 3 of them. Okay. Yeah, so basically what happens, whatever I'm giving you, there are only 4 kind of machines, these 4 kind of machines, but all these are based on classical physics. When we go to quantum version of everything. So there are 4 kind of machines for quantum. Okay, this was discovered in 2001 by Chris Moore at University of New Mexico. So he gave this idea about quantum finite automata, quantum push-down automata, quantum Turing machine. Actually, quantum Turing machine was invented in 1985. You know, on some of my YouTube videos, you can find more information about these things when I have given talk about quantum computing, you know, so then you can find more information about it. But quantum Turing machine, you see, so quantum Turing machine also has a limitation. Certain problems it cannot solve. Roser Penrose is a very famous mathematician. Roser Penrose and Stuart Hamroff. Stuart Hamroff is a doctor. I met both of them accidentally, or actually they invited me in 2003 to one of their conference, and where you know they are. Stuart Hamroff he has done a lot of experiments on near-death experience. You know, so while doing these experiments and while discussing with Roser Penrose, they came up with an idea that consciousness that we have in our brain is because of quantum Turing machine. Okay, so beautiful thing. That means your thoughts that are generated inside your brain is because of quantum Turing machine. And since each Turing machine has a barrier, quantum Turing machine has a barrier, in your life there will be certain problems for which you will never have an answer, right? This is the conclusion. You started believing on God, and that means, right? So that is a summary anyway. So can Turing machine solve all kind of problems? Answer is no. So there are another very interesting thing. $1 million problem, right, is P versus NP problem. Turing machines are of 2 kinds. The basic classification. One is deterministic and non-deterministic. So when you receive an input and if you have deterministic choice to move, that is known as deterministic Turing machine. And when you receive an input and you have multiple choices to move, that is non-deterministic Turing machine. So if you can solve a problem in polynomial time in a deterministic Turing machine, it is known as class P problems. If you can solve a problem on non-deterministic Turing machine in polynomial time, it is known as NP complete problem, NP class problems. So basically, it is not known whether P. So we know that P is a subset of NP, but whether it is not known whether P is strictly subset of NP or P is equal to NP. This is an open problem, $1 million. Okay, so if you can solve it, instantly famous, world famous, right? And you can solve this doing what? Playing a computer game. Minesweeper, have you heard of Minesweeper? Minesweeper, you can just note down T time problem. Minesweeper and P versus NP problem. You see the connection with Minesweeper game. You just play the game and earn $1 million, right? So that is the thing. Yes. Huh? Polynomial time is basically a polynomial, you know, right? So basically, when the input of the problem is usually size of the problem, you know, is a function of a polynomial. So I'll tell more about it later on, not now, but that much is enough. So second part of the movie is done. How much time is there? Or okay, fine. I think so. We will talk about it. So we'll talk about languages, and then we'll talk about deterministic finite automata. Then we'll talk about non-deterministic finite automata. Then I will talk about conversion between NFA and DFA. And that will be enough for you to attack assignment number 3, which has been posted. So I hope you will enjoy the beauty of computer science. Okay.